Hi students, welcome to my lectures on mechanical unit operations. Today we are going to discuss about the fluidization concept. It is very simple. Imagine a bed of particles are there in a packed bed. It could be any reactor, it could be any mass transfer process. So what is the minimum velocity I have to pump some fluid from the bottom so that the particles will be in floating conditions? What is the advantage of the floating condition? That means if the particles are in floating conditions, they are well separated. If they are well separated, almost all the surface area will be in participate in any reaction or any mass transfer operations. So it is important to fluidize the bed for certain chemical engineering applications. Okay, today we are going to discuss what should be the velocity of the fluid from the bottom is required to fluidize the bed. Okay, that is what the primary agenda. That's why our concept is called minimum fluidization, that is minimum velocity. If you give more than the minimum fluidization velocity, what is going to happen? The bed will expand. So let us go through the concept. Later on I am going to show you some video, and later on we will solve some examples along with the derivation of the minimum fluidization velocity. So if some fluid is flowing to the upward direction, okay, the drag will lift the particles, right, against the gravity of the particles. The gravity will try to push down, the drag and buoyancy try to push up. Okay, if the drag is sufficient enough from the bottom, the particles will be lifted and it will be floating in the fluid. It could be air, it could be water. So let me show you how the fluidization happens with a small experiment in the lab. Let us go to the lab. And this is the third one, which is called the fluidization assembly. In this assembly, you can see all the three forces acting on in a container. Here, and I have a beaker which is filled with a sand, graded sand. I mean, all the sand particles are of a equal size. Okay. Now the bottom, I have two. What is one inlet at the bottom, outlet at the top. The moment I pass the water with certain velocity, what happens? The drag is going to get increased. Okay, if drag is going to get increased, the sand particles will be lifted. Okay, after certain height, you can observe, the sand, which is a solid, now behaves like a fluid. That means it will have the fluid kind of property. It will move along the entire container because it has many industrial applications, because the fluidization has many industrial applications. We will see at the later what are the different applications as such. Let us see. I try to increase, if I start flowing the water from the bottom, see what happens. I have marked the initial length here, which is at the black, because this is the length of the bed, okay, from here to here. Let us see what happens. After certain point of time, you can see the bed has been lifted. Now you observe this, okay. If you observe, now the sand particles are behaving like that of a fluid, and bed height also got raised. Why the bed height got raised? Because the particles now, before the start of the experiment, all the particles at a very close distance. As I increase the flow, the particles, there is the spaces between the particles which is filled up by the fluid. Now this is called, you can see the particles are trying to come down, but the drag is trying to lift up, and buoyancy is also trying to lift up. So this is the important application of the fluidization, because there are many other applications. You can see more, if you surface area also available, because the particles get separated, more surface area will be available. So the moment if you keep a velocity which is higher than the fluidization velocity, what happens? The particles will go to the outlet, because I have maintained certain velocity so that the entire bed is in the fluidized condition. So this is how, and because of this application, you can transport solid from because beyond the fluidization, if you go, that's called as pneumatic or hydraulic conveying as such. Okay, this is what. Let us go to the board and discuss how to measure this kind of drag, gravity and buoyancy forces. Now you have seen what is the fluidization looks like. Let us go step by step derivation in finding the minimum fluidization velocity. First of all, you should do the force balance. The two upward forces are the drag and the buoyancy. The downward force is because of the gravity. This is the force balance, Fg equal to Fb plus Fd. From this, what is gravity force? Mass of the total mass of the particles in the bed, that is m bar p into g. This is the gravity. Buoyancy force is nothing but amount of fluid that is displaced because of the presence of the solid. That is what the mass of the fluid that is displaced by the entire particles in the bed into gravity. That is the amount of gravity, amount of buoyancy that pushes from the bottom to top. Drag. The drag is because of drag. When you try to have velocity, if you up the velocity from the bottom, what happens? It creates some pressure difference. The bottom will be at the high pressure because entire mass of the solids are trying to come down. What happens? The drag is trying to lift up. So there is a pressure drop from initial. It is a P1 pressure, and the upward is a open to atmosphere, or it could be anything P2. The P1 minus P2 is the pressure drop because of this drag of the fluid. So the drag force can be again simplified by delta P, which is P1 minus P2 into area, that is area available for the flow, which is called cross sectional area. Okay, Fd is nothing but delta P into A. Now let us go. Putting 2, 3, 4 in 1, I get 1 implies Fd is equal to Fg minus Fb. From this, if I substitute all Fb, Fb, Fd, Fg, and I landed delta P into A is equal to mass of the particles into gravity minus volume of the particles into density of the fluid into G. Okay, what is V bar P? That is total volume of the particles in the bed. Okay, what is the total volume? Volume is nothing but mass of the particles, total mass of the particles divided by density of the particles. Okay, simply substitute in place of V bar P, m bar P by rho G. Then if I simplify, I get delta P into A is nothing but m P by m total mass of the particles divided by density of the particles into G into density of the particles minus density of the fluid. Okay, rho F is the density of the fluid, rho P is the density of the particles. Then if I again simplify this, again mass of the particles with the density of the particles is nothing but volume of the particles. If you do some jaggery. So what is the total volume of the particles? The total volume of the particles is nothing but, if I want to calculate what is the total volume of the particles in the bed, I should know in the total volume how much percentage of volume is occupied by the particles and how much percentage of volume is occupied by the void spaces. That means if the voids are the spaces through which the fluid will pass. Okay, void volume is nothing but V bar total void volume in the bed, nothing but total volume into porosity. Porosity means empty spaces. In this total volume, if I know the fraction of porous spaces, the total volume into porosity will give you void volume in this bed. So similarly, volume of the particles is equal to total volume into 1 minus epsilon. That means epsilon is the empty spaces, 1 minus epsilon is the fraction of volume occupied by the particles. That is the total volume into 1 minus epsilon will give you volume occupied by the particles. Okay. Then if you put the equation 6 in equation 5, you get delta P into A is equal to V into 1 minus epsilon into G into rho P minus rho F. What is V? What is the volume? Total volume, it is nothing but area, cross sectional area into length. So A is the cross sectional area into length. You substitute here, you get this equation delta P by L is equal to G into 1 minus epsilon into rho P minus rho F. That is, this is the pressure drop per unit length. Okay, at a minimum fluidization conditions. Okay, this is the pressure drop, that P1 minus P2 within this length L. How much is the, how much? If you know G, if you know 1 minus epsilon into rho P minus rho F. This is the pressure drop in a packed bed at a fluidization conditions. Okay, we already know what is delta P by L. If you remember my last class, we have derived one equation, this Argon equation. So we can estimate delta P by L from the Argon equation. Okay, if I know the Argon equation, substitute the delta P by L, Argon equation delta P by L, and you cancel some terms, you get the equation in terms of velocity of the fluid, superficial velocity of the fluid. From that you can derive. Let us go to the board. Okay, this is the Argon equation. Delta P by L is equal to this much big equation that we have derived in the last class. Simply substitute the value of delta P by L in the previous equation number 8. Okay, if you do that, if you at minimum fluidization condition, okay, this delta pressure drop because of the packed bed is equal to the pressure drop that is caused in the fluidization. So equate these two equations, then this term is already, we know this is from the viscous forces terms, that is in laminar conditions viscous force dominate, then this is a priority and you can neglect this term. In the turbulent conditions you can neglect the viscous forces and go for the inertial or kinetic forces that dominate the system. Okay, in laminar as well as turbulent intermediate region you have to consider this both the equations. Okay, and what is epsilon m is equal to, because the porosity at the minimum fluidization, that means the empty spaces during the fluidization. Okay, because what happens if you slowly increase the velocity, the bed will start expanding, the porosity will change. So what is the exact porosity at minimum fluidization condition is called the epsilon m. Okay, VOM is equal to the velocity of the fluid at the minimum fluidization condition is called the VOM. So VOM is the superficial velocity required to fluidize the bed. Epsilon is the porosity of the bed at minimum fluidization condition, and if you cancel 1 minus epsilon term on the top, you get this is the final equation in terms of VOM. What is our objective? Don't forget our objective. VOM we have to find out, because here is one VOM, here is one VOM square. So it's not a straightforward equation, it's a quadratic equations. So you have to find out the roots of this equation to find out what is the minimum fluidization, that is what is the minimum velocity that is required to fluidize the bed. So this is what the problem, because it's a final equation that is used to estimate the velocity that is required. The problem, see the bed, imagine the bed having 8 feet in length, having the diameter of the particle which is nothing but, because let me read the rule, the bed of 8 feet containing particles of size 1.1 mm particle size is to be backwashed. That means this bed has to be backwashed from the water to remove the dirt. Okay, the particles have a density of 1.24 gram per cc, and the bed can be washed efficiently when used in a minimum fluid. That means if the particles are floating in a bed, it is easy to remove the dirt, because if the particles are very close by, it is difficult to remove the dirt between the two particles. That means it is better to fluidize the bed, okay, so that all the particles will be in floating conditions and easy to remove the dirt. Okay, if that is the case, given viscosity is given, that means the water viscosity is, and this is in pascals again, the porosity at the minimum fluidization condition is given, density of the fluid, density of the particles, sphericity of the the particles, diameter of the particles, and everything is given. You have to use the equation number 11, okay, to estimate what is the minimum fluidization condition. Okay, let us go to the problem. I substituted all the values in the equation number 11. I found out the final equation is in terms of V, that means some constant into V plus some constant into V square minus 2352 equal to 0. You can imagine it's a kind of quadratic equation in terms of minimum fluidization velocity, ax square plus bx plus c. So use this formula to find out the two roots. The one which is one appropriate for is a positive root. Okay, the velocity always in the positive, so that is you take only positive root. You know b A and C here, substitute all the values of B, A, C, and you get the minimum fluidization velocity that is required to fluidize the bed is 1.94 mm per second. If you pump the water from the bottom at the velocity of 1.94 mm per second, then the bed will be fluidized. So this is what the problem. The problem number 2, okay. What is the velocity that is required to expand the bed by 25%? Imagine this is your original condition, original velocity, because for you to fluidize this bed, you need 1.94 mm per second velocity from the bottom. Now the additional problem is you have to expand this bed by 25% more. Same bed, by increasing the velocity from the bottom, you can expand the bed by 25%. Okay, if that is the case, what is my velocity from the bottom that I have to put so that I can expand the bed? So for you to solve this example, you have to use some additional correlations. The first correlation is finding out the velocity, okay, provided if you know the minimum fluidization velocity. So the velocity which required to expand the bed divided by minimum fluidization velocity is equal to the porosity at the expanded condition. That means if the bed is expanded by 25%, the porosity will change, right? So that is the epsilon. Epsilon m is the given porosity at minimum fluidization condition. You have to use this expression VO is equal to minimum fluidization velocity, which you have already found out, into epsilon, that is new porosity divided by minimum fluidization porosity power 3.9. So you have to, if you know VOM, you know epsilon m, you don't know the new porosity. But for you to use the new porosity, this is the equation. The new porosity is equal to 1 plus 1 minus epsilon m into Lm by L. Lm is nothing but the length of the bed at minimum fluidization condition is Lm, and 8 feet plus 25% is called the new L. Okay, you know the Lm, which is L, which is the new length of the bed, is original to this 8 feet plus 25% of this 8 feet. Okay, that is what new L is equal to 1.25. Okay, because 25% extra, right? L equal to 1.25 Lm. So if you substitute these values, you get the new porosity. Once you get the new porosity, put it in this equation, evaluate new velocity that is required to expand the bed by 25%. So VO, you know, from the calculations I have got 5.4 mm per second. The minimum fluidization velocity is 1.94. If you still want to expand the bed beyond this minimum fluidization, which is 25% more, then you have to increase the velocity from 1.94 mm per second to 5.41 mm per second. These are, I hope you understand the lecture. Okay, I will come up with a new video because it's one of the important concepts in the chemical engineering. Okay, see you.